Morning, everybody. Yes, welcome again to Big Data. Hopefully, everybody had a good weekend, good Mondays. I saw, well, yeah, so with my kids, like to go to, so CMC has faculty housing that's just south of the campus that we live in. So whenever we hear, whenever there's sports events, we hear all the cheering and things, and often take my kids to them. So we saw rugby and some swimming and some track and field events going on. That was fun. Hopefully, you all also had fun weekends. Today, I'm on a topic 6 folder that has been added up here to our class repo. And I'll go through some announcements here in a second. There are 3 handouts that I have printed out up here that you're welcome to come up and grab. As we get to they're sort of like where they're at in the GitHub repo is scattered a little bit all over the place. So as we get to the spots where it's talking about those, I will point out where they can be found in the GitHub repo to follow along electronically. We'll start with some announcements today and then get into technical stuff. So first big announcement, I guess reminders, your homework Pagilla 2 not due today like it normally is on Tuesdays, instead due on Thursday. And also on Thursday, you'll be having the quiz on the material from last week, the subqueries and the joins. And I'm not happy with how our discussion of the outer joins went last week. So the way we'll start class today is finishing up that discussion of the outer joins, and that'll use some of these new handouts. Then that shouldn't take all of our time today. We'll start on the new material here for this topic 6, which I'm calling schema design, and have some more quick announcements here about timeline, assignments, things like that coming up before spring break. So you will have one more homework assignment before spring break. And to give you, since I extended the deadline for the one this week, I'll extend the deadline for the next week one as well out to Thursday instead of Tuesday. So I'll have that homework posted this Thursday, so I have a week to work on it. There will be one more quiz next Thursday, and then the midterm exam. The midterm exam will not be cumulative. It'll just cover the things on SQL, so the SQL 1 topic, the SQL 2 topic, and the schema design topic that we're going to be covering in topic 6 here. And so in particular, none of the Docker or Shell or Git things. You won't be tested explicitly on that in any way. The format of the midterm is that I've designed it to take roughly less than an hour, I think, but you won't have any time limit. So I will give it to you on next week on Thursday after class, and then you'll have 10 days to complete it whenever you would like to before the end of spring break. And we will also the Friday before spring break not be having our lab section, and my recommendation on when to do the midterm is to use that lab time to complete the midterm. And if you do that, then you won't have any assignments at all over spring break. So that should be all of the, upcoming due dates, anything administrative happening before spring break. Are there any questions about anything timeline-wise, administrative? Yes.
So for the midterm, it's going to be just like a Pagilla assignment, but can't consult anyone.
Yeah. So the question is on the midterm. It will be like one of these Pagilla assignments that I'll have a handful of prompts for you to write the SQL code for. The differences are, no collaboration in any form at all, and I'm not going to give you the expected output as well. So you'll have to go just from the English to the output without having this expected sort of to guide you. The grading for it, I'm also not going to grade it by just doing a diff and seeing whether you got it exactly right or wrong. I will manually read through all of your answers and see if you got the main idea or not got the main idea. And minor things like column order or column names, subtle things like that would break a diff are not going to be important for the midterm grading. Yep, good question. Any other questions? And yes. So there will be no test cases provided, correct? For the midterm, yes. Any other questions? Anything administrative? Yes. Question A is, will it be on paper or electronic? I'll provide you with a GitHub repo similar to the Pagilla assignments. You'll be allowed to use your computer, encouraged to use your computer to complete it. And then you'll submit a link to your completed assignment on Sakai. Okay, great questions. That's it for our administrative stuff today. We will again start today by finishing going over the outer joins from the SQL 2 notes. That'll take us, 20 minutes, half hour or so, and then we'll start on this topic 6 stuff up here. Electronically, where the files are that we'll be looking at inside of our SQL quiz folder, there are several new files. The main one is this join notes.sql. That's the big stapled packet up here. And there's also a truthtables.sql file right here that we'll take a look at in conjunction with this join notes.sql. Those will have more help for us on the material from the previous topic. And then we'll start talking about this quiz notes 3.sql, which will not be on the quiz on Thursday at all, but midterm material and next week quiz material. So we'll take a look. I'll switch over to the terminal here in a second, and we'll start by taking a look at this. Actually, we'll start by taking a look at the join notes.sql file. Before I do that, I'm going to jump over here to the topic 5 and remind ourselves in this joins section where the sort of notes or textbook for this material is. So again, section 3 of the postgrestutorial.com has a good sort of intuitive explanation about what all the different types of joins are. And this link right here has a more technically correct explanation about what the different types of joins are. And I'm just going to really quick scroll to the bottom of this link, and you would see something like this that looks somewhat similar to some of the SQL statements that we were talking about last times in terms of the technical definitions of the outer joins, the left and right joins, where you have some queries and there's unions and accepts, these set operations. This is the reference that goes over that material in detail. Let's see. I want to come back over here, but Firefox is not responding for some reason. That's okay. We'll jump over to the probably this is it. Make sure I'm sharing my screen again to allow probably some sort of hiccup with the internet there, but hopefully that's fixed now. And now we're on to, I'm in my SQL quiz folder over here, and we're going to take a look at this join notes.sql file.sql right here. I'll open that up in Vim, join notes.sql. And actually, I want to change my screen here to be side by side. And so over here on the right-hand side, let's set my prompt equal to just the $sign now, so it's not taking up my whole screen. And I'll move that thing over here. So on the left-hand side, I have the notes file opened, and then on the right-hand side, I have a terminal that I might type some SQL commands in here in a little bit. But the idea of this notes is, again, it's going to go into a little bit more detail on the outer joins. It has a simplified version of the data from the quizzes. So down here under these create table commands that I have listed, what we call the schema of the database is the same. These create table commands are the same, but the data inserted has just less data now, so that we can actually visualize everything that's going on the screen at once without having to scroll back and forth about things. And so this will capture this smaller data set will capture most of the edge cases, the interesting edge cases for us to talk about. But again, on the quiz on Thursday, you'll have to consider how those edge cases might interact with these other commented out rows as well. And there's two really common sources of errors. So in particular for students on the quiz, a common source of error, but also in general for programmers in real life doing real things, common sources of errors with joins. And that's what happens when there are duplicate rows in your tables and related to the behavior of null values. So we're going to, as we're walking through today, explicitly be emphasizing those things. And you'll notice in particular that in the basket A, we have these two duplicated rows here with apple and 1, the null value down here, and then this sort of in basket 2, this kind of partially duplicated row that the fruit is the same, the IDs are different, and then still a null value down here. And so we'll be paying careful attention to how all of those things are going to behave as we're going through things. Any questions on the setup, where we're at, what's going on? Yes. Question is, where is the file that I'm looking at right now? And the answer is in my the SQL quiz repository. There is an electronic file, this join notes.sql file. And this is the name of the file that is the big stapled packet up front. Okay. First sort of join that I have listed here is a cross join. Again, it has this, this comma right here, so that makes it a cross join. And for all of these queries, I already have the final output down here just printed out so that we can take a look at it without worrying about if the SQL commands are being typed in correctly or not. But just to follow along a little bit, I'll open up on the right-hand side in SQLite this join notes.db file created by passing in the join notes.sql file like this to create the tables. If you run a command like this, input redirection on the SQL file, that will create a database file that you can work with. And now if I do this cross join like this, you see that the output down here, I guess it's not quite formatted nicely yet. Let's change the mode to Markdown so it'll be a little bit nicer to look at. And Control D, recopy and paste this thing right here. And re-go into SQLite. There we go. Now recopy and paste this thing. Now re-enter the mode of Markdown. Now recopy and paste this thing, and we get the results down here that look like this over here. So I already have the output of all of these commands listed, so we can just look on the left-hand side over here for the most part. And again, cross join, what's going on, each row in the left-hand table gets duplicated once for each row in the right-hand table. So there are these 4 rows on the right-hand table for A, and we duplicate those for the left-hand table for each of those rows. The minor syntax thing that we didn't explicitly cover last time is that if you have a join by itself like this is an inner join and not a cross join, but the inner join has no condition over here, has no on condition. So this is the equivalent of the on condition over here being like just true. So what I have right here is equivalent to on true over here. And again, this on condition, all it does in the inner join is it applies a filter on the cross join to remove some of those rows. So if we have our cross join as always being, or our inner join condition as always being true, then we're going to take everything from the cross join and not remove anything. And so this inner join happens to have the same exact output as the cross join above. Again, all of these like weird problems, when the weird things come up, the thing that you'll always have to do is go back to these, the syntactic sugar, this understanding of everything comes from the cross join, and then work step by step to rebuild things out. Any questions about what's going on so far? Just the mechanics of what we're looking at? Okay, almost into more interesting stuff. Down here now we'll have an example of an inner join on the ID column here. And so I now have this inner join right here, but there is an explicit on clause, and the on clause is checking to see that the ID in basket B is equal to the ID in basket A. And the way that I've written this down here to make it easier to visualize is that this is like the output of that diff-u command. So this is the output of diff-u. So the -u making it the human readable that we talked about for debugging your SQL test cases between the cross join and whatever the command up here is that we're looking at. So in this case, the cross join and the inner join, the join by itself. And so the minuses over here indicate which rows the filter does not become true for, and so these rows are the rows that end up getting removed. So here, our condition that the 2 IDs must be equal to each other. If the IDs are not equal to each other, so in this case, 1 not equal to 2, that line gets removed from our results. 1 not equal to null, that line gets removed from our results, and so on. Again, very common way to miss points on the quiz is make a mistake about duplicate rows right here, where we have duplicate rows right here with Apple appearing in, do a select star from basket A over here, Apple appearing twice with ID 1 appearing twice over here. Very easy to forget to apply that in your joins and only have it appear once in your outputs. The key formatting thing here is just the minuses indicating what rows are being filtered away by the inner join here. And this is all hopefully review from the very first week of material that we talked about. The interesting stuff, this is going to happen next here with the left join. The only thing that's different about this problem right here and the previous one is that I've changed the inner join to a left join. And now the left join is equivalent to an inner join where we add some stuff. And so the inner join down here is all going to be exactly the same. That we're still removing the exact same rows down here because we are still removing the exact same rows because our condition up here is exactly the same. So the left join will always have everything that the inner join has. Similarly, a right join or a full join will always have everything that the inner join has. What's going to be different is that the left join is going to add some new rows. And so to illustrate that, I have a plus down here about that this line is getting added from the left join right here. And so this line does not appear anywhere in the original cross join. So where does it come from? The idea here is that in the left join, we want to somehow capture all of the rows that from the leftmost table here, basket B, that were not included at all, that somehow got filtered out of this condition over here. So the rows that we're currently capturing are this 1 apple row and this 2 apple row. But if we look at the null pair row down here, we can see that all of the null pair rows, all of them have a minus next to them. So all 4 of these are getting filtered out. And so because all 4 of these, everywhere where in the cross join, we have a row that comes from the null pair row in the original basket B table, all of these 4 rows are getting filtered out. We add only 1 new row for that particular row, the null pair row from the original table. In order to complete the sort of the type of this row so it matches with the table, null values get added over here in these 2 columns. Null values get added from the basket A table. So one way of thinking about the left join here, or any of these outer joins, is that any row from the leftmost table, any row from basket B that did not get included in our join, that did not match this join condition for whatever reason, will get added down here as a new row with null values everywhere in the basket A table. And the key thing right here is that this plus is the new row not appearing anywhere in the cross join and coming because we're doing the left join. Are there any questions about that so far? Yes.
Why was the ID of Ruby also added as a null?
Question is that here we have a null for the ID column of the basket B table. That both of these columns right here come from basket B, and both of these columns come from basket A. And when we think of the left join, one of the things that I said is that all of the columns corresponding to the basket A table that correspond to the thing on the side over here that we're not doing the outer join with. So when I say left join, the outer part of this join goes to basket B, and basket A remains only as an inner part of the join. The basket A columns over here have to get filled with null because we have to put something there in order to make it sort of type check so that we can put a row in this table. And the question is that makes sense, but where did this null value right here come from? Why did we add a null value to the basket B ID column over here? And the answer is that this null value right here is not something that we added. Instead, what happened is that the original values in the basket B table was null comma pair. To verify that, on the right-hand side over here, I'm going to run the select star from basket B like this, and we'll see that we originally had a null pair row like this. And so that's where this null comes from, is that it was in the original data from the basket B table. And so we have to copy it down here as part of the procedure of just capturing that this row was not inside of basket A anywhere. This row did not satisfy this join. Did that answer your question? Good question. Yes?
Just to clarify, if there's a null ID in basket A, we're doing a left join, then the null ID will be mapped to any null ID in basket B, so like it will be multiple.
Your question is over here, if the ID right here is null in basket A, what's going to happen?
Yeah, so like if there were like multiple null IDs in basket B, would it have to all of them?
So the question is here, what would happen if we had multiple null IDs in basket B? Let's do a quick experiment to check that. I will do an insert into basket B, values, null, comma made up. So we know that it doesn't match anything. And redo this select star. And so I think this is matching what you're asking about, is that there are multiple null values over here. What's going to happen, and the thing to always keep in mind as you're working through these problems on the quiz or on homeworks or anywhere in real life, is that the outer join, the left join, always starts as an inner join. And so when we do the inner join here between this new table right here and our basket A with this new value right here, what's going to happen is that this new row right here will never match this condition right here, because our new row has a null value on the ID in the basket B ID column. That this right here is a null value right here. And so null equals something will always evaluate to null, will always be equivalent to false, no matter what happens in basket A. And so this row right here can never get added into our inner join. That means when we do the outer join, this row right here is never part of the inner join, so it's always something that we have to add as part of the left join procedure right here. Because again, the left join procedure is first do the cross join, then do the filtering like an inner join, then add any extra rows that were not appearing in the inner join. And so because this will never appear in the inner join, it's always going to have to be added extra, no matter what is in basket A. To verify that, I will, let's see, I'm going to copy and paste this command up here and run it, and we'll take a look to see what the new outer join looks like. But in order to copy and paste it, I'm going to turn off my number, set no number like this, copy and paste this down here, hit enter, and you can see now we have 2 additional lines that have been added down here, the pair line corresponding to this line right here, which is from our original data set like this with the null pair like this, and then the new made up line right here that also was added down here from this. Again, the reason we have this line right here is because this line right here does not match the join condition, and so this line needs to be added down here. I'm not sure if that answered your question. Okay. Yeah, it's, again, very easy to think you have it understood and then suddenly think about some weird edge case that makes everything like go in doubt for you. And so the working on these problems, understanding what's going on just takes a lot of typing things into SQL, making up like edge cases like this, predicting what's going to happen, and seeing if you get the correct answer. And again, the notes have lots of problems like that I encourage you to go through and try to figure out. The difference, we're going to move on to the next problem now. The difference between this problem and the next problem down here is we just changed the left join to a right join. And when we have a left join, the extra sort of information that we're adding is always going to come from the leftmost table. So here, the extra row that we're adding down here comes from the basket B table. The additional information in order to fill out the columns in basket A on the right-hand side over here are guaranteed to always be null because it's a left join and this is appearing on the right side. In a right join, it's just everything is reverse. That we will, if we come down here, look at the new line that has been added right here, look at the new line that has been added, then this information over here, cucumber, is coming from the basket A table on the right-hand side. So it's a right join, so the new information comes from the right-hand side of the table. And the information on the opposite side of whatever direction we're joining is always guaranteed to be null. Like we saw last time, though, just because it's a right join and the information on the left-hand side is guaranteed to be null, we could still have null information on the right-hand side. That this information right here in this column right here in the cucumber row is null in the original data. Again, if I do a select star from basket A, we can see that the ID is in fact null in the original data. And so we do, in fact, still have a null here. The fact that there's a null here is not coming from the fact that we're using a right join or one of these outer joins. Instead, it's coming just from the fact that we have a null in the data over here. Any questions so far? Okay, there's another example down here on joining on fruit instead of joining on ID. So the interesting thing about doing it on fruit instead of ID is that the fruit does not have any null values in any of the columns. And so you have to think a little bit differently about what's going on here. But again, the general procedure is always the same, that you start with the cross join and then filter things out. And again, extremely easy to miss points on the rows that have duplicate entries. So this, like in the basket B, there's duplicate fruits now inside of the fruit B column. And inside of basket A, there are duplicate fruits in the fruit A column. Very easy to lose track of those duplicates. And so definitely make sure you're paying attention to the duplicates on the quiz. Very common way to miss points on the quiz. So that's the inner join. The left join, again, is adding some new rows, and the right join also adding some new rows down here. In this case, it's adding 2 instead of just 1. Let's see, this last sort of problem in this set is introducing the idea of the full join, and the full join has both a left join and a right join together. So the full join, again, starting from the cross join, doing the filtering out, removing lines that do not match the fruit B equals fruit A condition. So for example, these 2 lines being removed because the apple does not equal to orange and cucumber. Similarly, all of these lines being removed down here. The left part of the join matching the pair from basket B, getting this particular row right here. This particular row right here from the basket B table, that's happening from the left join, but we're still filling the right-hand side with null, and then the right join portion getting the rows from the right-hand side, the basket A table in this case, and filling the left-hand side parts with null. So the full join, not too bad once you wrap your head around the left and right joins. It's just doing one after the other. Any questions so far? Yes.
So is a right join equivalent to a left join just with the order of the hit?
Yeah, this is a fantastic question. And anytime you're thinking about any of these SQL problems, this is the exact type of question that you want to be asking. So the question is a right join on basket B, basket A equivalent to a left join basket A, basket B? That if you were to change right to left right here, is it the same thing if you swap the order of the tables that you're joining? And the answer is yes. They are identical up to the ordering of the columns. That the column order will be different because just like in the cross join, the column order is different when you cross join, change the order. But otherwise, they're entirely the same. So anytime you could use a left join, you could also use a right join. It's sort of traditional to prefer using a left join. Left joins are probably 99% of the outer joins that people use. So again, outer joins are these left-right full joins. They're called outer because they're adding things to the cross join instead of just removing things. The left join, by far the most popular in practice to use, but the right join is also equivalent to that. The full join, not equivalent because it's doing both of them at the same time. That answer your question, Oliver? Okay. The sort of intuition about going on to the next session here, this intuition about the left and right joins especially the things that were probably explained to you in like the Foundations of Data Science course, if you took that and saw SQL in your version of the course. The intuition there is that the left and right join is doing something very, very similar to this like is not with a subquery. That I've been talking about, like these rows down here, these things that were being added, like this left join right here. I've been talking about this in a way that like we add this row because it did not appear in the inner join up here. And last time we talked about the way that you one way that you can formalize this idea of not appearing in another query is by using this not in and a subquery operator. So we're going to go over these two queries here, go back and forth between them, talk a little bit about why they are equivalent in this case and seem to be equivalent overall. And then we'll talk about weird edge cases that cause them not to be equivalent and cause this intuition to break. So I'll start with this bottom one down here, that where we're selecting all of the columns in basket A. And now if we look at the select clause up here, we can see that this is also selecting all of the columns in basket A because we have the star and it's qualified on basket A up here. The from clause over here in the top one includes both basket B right joined on basket A, and down here includes only basket A. So the reason in order to make the columns match, we have to qualify the star up here is because there's also the basket B columns to consider as well. So select star from basket A. And we want to get all of the fruits that were not in basket B. This is, again, like intuition about what's happening in this outer join query up here, that we were joining on the fruits, fruit B equals fruit A. And here, this pair right here is being added because pair does not appear anywhere in basket A. It doesn't appear anywhere in basket A, so it never matches this condition. So this row does not get included in the inner join, and so it gets added. Similarly, in basket A, we have the orange and the cucumber fruits. Orange and cucumber never appear in the fruit B over here, and so orange and cucumber are getting added over here. So that's the intuition about why we're getting orange and cucumber when we're doing this outer join, and this sort of not in operator is just another way of specifying something very similar, that we want all of the fruits in basket A that are not in basket B somehow. And in this particular case, these two queries are the same. They give us the same results. In general, though, this not in operator is sort of a dangerous way of doing this kind of selection because of how things interact with the with null values. And the next example down here is going to explain why that's the case. So this next example down here is going to violate our intuition about why the outer join is doing something like finding rows that are not in another table. The outer join over here, these two queries that I have, they're the exact, basically the same idea as the previous queries, but now instead of joining on the fruit, I'm joining on the ID. So I want to find all of the rows in B where the ID is not equal, where the ID in B does not appear in A somewhere. And in this case, this is the only row that matches that idea, where we have this null ID down here. And the intuition, again, is breaking because we have null values down here. Looking at our fruit A table, so we have the query open down here, we do in fact see that we have a null value right here in the basket A table. And so there is, in some sense, something that matches this row, but because it's a null value, the equality is not going to check out, and we will keep this row. If we were to actually just use this query as it is, so like actually using the not in operator, we would get that actually nothing gets returned at all. This query has no rows that are returned. So I want to walk through step by step about why that's the case here. why the not in operator cannot be used here instead of the left join to capture this difference. If the first thing we'll do is take a look at this subquery right here where we do select ID from basket A. When we do that, you'll see that there are, in fact, we get this null value right here inside of basket A. So again, this null value right here in basket A coming from the cucumber row. And so when we do the expression where ID is not in select ID from basket A, again, the not in operator, this is syntactic sugar for a bunch of ands gluing things together. And so we have ID not equals to 1, and ID not equals to 1, and ID not equals to 2, and ID not equals to null. All these values that I'm chaining together right here are just the values that we got from our select ID up here. And because we have ID not equals to null right here, this is always, no matter what ID is going to be equal to, this entire thing right here will evaluate to null. One of the things that I've sort of glossed over previously is how the and the ors work with null operators. And it turns out the and, if you have a null on one side, I can never evaluate to true. I'm going to switch my tab over here on the left-hand side to go over to this truthtables.sql file. This is one of the handouts, one of the one-page handouts over here. And in this truthtables.sql file, just to illustrate how explicitly how the ands and the ors and the nots operate in SQL, I've created this table called bool, inserted the values true, false, and null into those values, and we'll just look at the outputs down here of what happens. So the not on 1 evaluates to 0. In SQLite, 1 is equivalent to true, false is equivalent to 0. It doesn't have its own Boolean type, so it uses integers to store these. Again, this is the sort of Python way of storing numbers, but it's backwards of the C and the shell way of storing truth and false values. But the not mostly behaves like you would expect. The next row problem down here looks at the and operation. So this is the one that our syntactic sugar was just looking at. And if we have a null value here, for example, and no matter what we are combining it with, if we do a true and null, or a false and null, or a null and null, we cannot get a true value out here as the result. We can only get null or false out here as the result. And whether we evaluate to null or false, that's inside of a where clause. Those are equivalent because they're not true. And so we will never capture any of the rows from this line down here. There are some ways that you can try to modify these subqueries, but it's, for example, by adding an is not null down here in the where clause, so you don't get this null value down here. But if you try that, you will see that it still does not work, that it requires a lot of fairly complicated manipulations in order to get your null values correct if you're using the not in sort of version of this type of query. So the takeaway point from all of that, again, so on the quizzes, you'll be responsible for understanding both just reading a SQL query, what's going on. On your homeworks, you'll have to write both versions of the not in and the left join operations for certain problems. But on the, like in the real world, people would always prefer, experienced SQL users would always prefer to use this left-right strategy, left-right joins, to capture rows not in another table. They always prefer that over the not in plus the subquery pattern, because the not in plus subquery pattern is likely to run into subtle bugs involving null values. Any questions about any of that? Okay. One last thing then to talk about your quiz, this complex join clause. There is no sort of intuition that you can possibly fall back on if you have any sort of outer join and a more complicated join clause like this over here. You have to just rely on going like, what is the definition of all of my, of whatever particular join that I'm using. So in this case, comparing the IDs for greater than, first doing the filtering for the inner join, and then manually finding which rows were filtered out and which ones in each table and adding those back in. There is no like easy to grasp intuition on something like this, and you can definitely count on there being at least one fairly obnoxiously hard problem involving outer joins and some complicated condition like this. Okay, oh yes, there you go. So the question is, on our join over here, we have basket b.id greater than basket a.id, and let's just walk through what exactly is going on here. So this first row is everything is getting filtered out from when we have one apple on the basket B side over here, because we're looking at this ID 1, and 1 is the smallest of all of our IDs, so it can never be greater than any ID on the right-hand side, including it can never be greater than the null ID over here. That 1 greater than null evaluates to null. So all 4 of these correspond to the first row in the basket B table on the left-hand side of our full join over here, and all 4 of these get filtered out. I can immediately jump down over here now and say that 1 apple, because it got filtered out from every possible combination, it never got included. It's definitely going to get included in the left join down here. Then coming down here to the 2 apple row, we can see that these 2 lines get added because 2 is greater than 1. So we do keep these 2 lines here, but we're not going to keep these 2 lines down here for the same reason, because 2 is not greater than, it is greater than or equal to 2, but it is not greater than 2. And our condition up here is specifically greater than 2. And so both of these lines being filtered out. Because we are including at least one of these lines involving the 2 apple row, we do not include 2 apple down here in our left join rows. But the pair row, because it has a null value over here, it can't possibly be greater than anything, so these all get filtered out, and the null pair row getting added down here as part of the left join. Figuring out what things get added as the right join over here is a little bit more complicated because they're not all nicely grouped together, but if you work through all of the rows, you'll see that 2 orange, every time 2 orange appears, it has a negative next to it because the 2 is the largest number in this particularly small data set, and so it can't possibly match anything. Similarly, every time we have a null in one of our rows, so null cucumber, that can't possibly be less than anything because it's a null value. Null compared to anything, no matter what kind of comparison you're doing, is null, which never evaluates to true. And so we must also get this in our final output down here. Did that answer your question, Nico? Yes, Ben.
Clarify, is everything like this and everything in the packet for this week's quiz or next week?
Yeah, great clarification, administrative question about which material, which quiz this packet is related to. This is all information on the quiz 2 materials. So this is a clarification of the information in the quiz notes 2.sql file. Down where it talks about outer joins, anything from the quiz notes to SQL file, fair game for the quiz on Thursday, and this is a subset of this stuff over here. Okay, that's a good segue for us. Now we will transition to things that will not be on your quiz on Thursday, but will be on the quiz the following week. And what we're going to talk about here, so we're going over to the topic 6 folder again in our repo, and we're going to be talking about actually designing the database schema. So we've used this word schema a bunch of times in the class so far. It roughly means what your create table commands are doing, and we're going to start talking about why you might create your tables in certain ways. Scroll down here to the actual lecture. So databases get very complicated very quickly when you have real world data, and understanding those databases can be very, very tricky. So the sort of goals, why we're talking about this, maybe the most straightforward thing is you've been starting using this Pagilla database a lot. We'll see talk about why it's actually designed the way that it is, some of the alternatives about how it could have been designed, and the pros and cons of those alternatives. That will also help you start thinking about why, I don't know, getting some intuition about types of SQL queries to use in certain situations. More concretely, the first task that we're going to talk about is actually measuring the disk usage of a database. So how many bytes do each of these tables take up? That'll give us some very obvious motivations for why you might design your create table commands the way they are. One of the things that we're going to see is that there's a lot of overhead in Postgres in particular. We'll see there's two main types of overhead. We'll talk about the row overhead in this topic, and after spring break, when we're talking more about efficiency, we'll talk about this page overhead. Both of these are going to be closely related to efficiency things in SQL that we'll be talking about again after spring break. Another thing that happens when you're designing your schema, your create table commands, is that there will be almost always redundant data in your database somehow. We'll talk about how to deal with that, potentially how to remove it from different places. And we'll also talk about how the database schema specifies what correct data should look like. And we'll see that Postgres enforces that a lot more than MySQL or SQLite does. That's high level what we're talking about this week and next week. Some quick important quotes. So Fred Brooks, author of this famous software engineering book called The Mythical Man Month. The sort of basics cartoon version of this book is that business people often think that if you have a problem where one person can solve it in 10 days, then 10 people should solve it in 1 day. And he argues against this. One of the main other famous quotes from this book is, "Show me your code and consider your tables, and I shall continue to be mystified, but show me your tables, and I won't usually need your code. It'll be obvious." So for these databases, very rarely do documentation of databases include, for example, SQL queries. It's almost always just these diagrams about the schema, and then everything should be obvious from that point. Linus Torvalds, another famous programmer, author of the Linux operating system and the Git version control system. He says, "I will in fact claim that the difference between a bad programmer and a good one is whether he considers his code or his data structures more important." So data structures here, basically the same as the schema of your database, whether you consider the code or the schema more important. That bad programmers worry about the code, and good programmers worry about the data structures or the schema in their relationships. So we'll see many examples about why that's going to be the case. Both of these things the case here in the next 2 weeks. And then a totally unrelated quote, but one that is maybe interesting to students, from Google's vice president in charge of hiring, maybe related in terms of the midterms coming up. But he said that GPAs are worthless as a criteria for hiring, and test scores are worthless because they don't predict how productive an employee will be. And so there's a whole New York Times article on Google's philosophy of hiring, if you are interested in reading that. Okay, on to the technical details. We're going to be talking about this idea of row overhead in class today, and we'll be using our third handout in class in the SQL quiz folder. This handout is the quiz notes 3.sql file like this one right here. And I am going to see if I can get my screen organized. I'm going to have it open on one side of my screen, and our class notes opened on the other side, and we'll go over both of these two things simultaneously. So on the left-hand side over here, I have again, looks like I misnamed the file up here. It should be quiznotes3.sql file. And then on the right-hand side, I'm in the row overhead section of our class notes. We'll start by just going over, so this quiz practice 3, your next week's quiz is going to have a different format than this week's quiz and the previous week's quiz. Your format for this week will be the same as last week, where you'll have 4 different problems. For each problem, you'll have to provide the SQLite and the Postgres output. For next Thursday's quiz, instead of providing the output of SQL commands, you're going to have to tell me how many bytes a particular row is taking up in a Postgres database. I'll have 2 different create table commands for you, and then 2 different insert commands that correspond to those create table commands. These notes here have more examples than just that, but your final quiz will only be 2 create tables and 2 inserts. Another difference about the format of the quiz next week is that you're going to actually have access to the internet, to a computer, in order to complete it. We will see that this is what we're going to be talking about right now is not something that's reasonable to do in your head, and you'll need to be able to look things up. So the quiz will in part be testing how well you can look things up in the Postgres documentation to find the information that you will need. Okay. We're going to, in order to, so the format of each of these problems is each insert command corresponds to an individual problem, and we will walk through this. We'll start by walking through this first insert command right here. How many bytes is this actually taking up in our database? That's the thing that we ultimately care about. How many bytes is this thing right here taking up in our database? My cursor, yes, it does work. And I will be going again back and forth between the right-hand side and the left-hand side in order to do that. So back over here to the right-hand side. So again, you're responsible for being able to calculate the number of bytes used by a row of data in Postgres. References, there's these 2 sort of detailed references over here. Again, you're not required to read through any of these, but these 2 in particular, I encourage you to read through them because they will contain SQL commands that we're not going to cover, that if you run those, and you would be allowed to run those on the quiz, they will just tell you the answer. It will output the number like 42, whatever the answer is, and you can just write that, and that's it for the quiz. So if you read through those, then you'll get a command that just tells you the final answer for these problems. In class, we're going to go through how those commands are actually working and where these numbers are coming from. Postgres sort of has a reputation for having more overhead than other databases. I think if I refresh my page here, another couple of lines of notes might come up. Yes. Nope. So right here. So Postgres has this reputation of having more overhead per row than other databases. So it's partly due to Postgres's emphasis on like simplicity and correctness over efficiency. So SQLite and MySQL in particular, having the emphasis on like ease of use and efficiency. Postgres more emphasis on simplicity and correctness. And so we'll see there's a little bit more overhead because of that. And you will not be responsible for the details of any of those other databases, just for Postgres. And that's both for the quiz, midterm, the entire rest of the course. You'll only be responsible for the details of how Postgres is storing things on disk. Okay, we're going to walk through now problem 1 here, starting with bullet point 3. It's going to tell us exactly what to do step by step. Before I do that, though, any questions about where we're at, what we're doing, why we're doing it? Okay, so every row, every insert statement is inserting a row over here. There's 1 row being inserted. So every row is going to start off with a header section, followed by a data section, followed by something called a padding section. So when you're working on one of these problems, just going through, computing the size of each of these, and then adding it up is the thing to do. So we'll start with the header section. The header contains a 23-byte structure called the heap tuple header data. And if you click on this right here, it's going to take you to the Postgres documentation about what exactly goes into this heap tuple header data structure. Again, post spring break, we will be going through all of these details and what they are. At this point, all you need to know is that it is 23 bytes in size. And then after this is this thing, this optional null bitmap. So over here on the left-hand side, I will do my sort of arithmetic notes up here in this little blank space for this individual problem right here. But starting with the header, it's going to start at 23 bytes for this, this heap tuple header data. The next thing in this header is what's called the null bitmap. And the null bitmap is only present if the tuple contains at least one null value. In this case down here, we do in fact have one null value right here in this row that we're inserting. And so the null bitmap will be present. In the null bitmap, we use 1 bit per column, and that's whether the column is nullable or not. These individual bits are going to be storing whether that column has a null value inside of it or does not have a null value inside of it. And so that's why we need 1 bit per column. In this case, we have 1, 2, 3, 4, 5, 6 columns. So we use 6 bits overall for our null bitmap. By default, every column is what we call nullable. So nullable means that it could possibly contain a null value inside of it. Inside of the create table command down here, both this column right here and this column right here, these are equivalent syntaxes. These mean that we can, in fact, store null values inside of A or B. If you have not null after the particular column over here, the not null signifies that you cannot store a null value inside of column C. It doesn't matter, though, in your schema, whether you specify null or not null, whether the column is nullable or not nullable, it still is going to take up space in your null bitmap. Modern computer architectures, you never store things inside as just bits by themselves. Instead, you have to round up to the nearest byte. And bytes are 8 bits. And so this 6 bits for the null bitmap is going to become 1 byte for our actual our null bitmap itself. And then adding those two things up, we have 23 bytes. I'll actually put the unit here. 23 bytes for our original struct, then 1 byte for this null bitmap, and that gives us 24 bytes overall. One last thing to do for this header, and that's that the header must be padded to a multiple of 8. And in this case, 24 is divisible by 8, so we're done. And it turns out that anytime you have a table with less than or equal to 8 columns, then you'll always exactly end up at 24 bytes. And so the header almost always will be 24 bytes. If you have more than 8 columns, then you can potentially, your header be larger. And so if you have, in particular, anywhere from 8 to 264 columns, you'll have 32 bytes in your header. That's all, again, because the null bitmap is getting larger. And then once you get past the 24 bytes over here, you have to round up to the next 8 byte in size, which goes up to 32 bytes. But in this case, header 24 bytes. Any questions? Yes, Abhizer. The question is, how does the header relate to the column names? The answer is that actually the names of the columns, so like this ID, A, B, C, D, E thing over here, these are not stored anywhere in this information that we're talking about. What the actual contents of this header are, if you're interested at this point, you can take a look at this documentation over here. We will be going over this in detail later on, but at this point you don't need to know like what's actually contained in these 24 bytes. You just need to know that there are 24 bytes, 23 coming from this black box thing over here, and then the last byte coming from the null bitmap. Again, the only weird thing that can happen in the header part is that if you have more than 8 columns, then you could potentially overflow this 24 bytes, and then you'll have 32 bytes if you have more than 8 columns. I don't know if that answers your question or not.
Yeah, about null bitmap. The null bitmap would just mean that there is a null value and there is a null bitmap.
So the null, the bitmap means that it's like a list of zeros or ones, a list of bits, and the semantics of those zeros and ones are whether there is a null contained in that column or not. Yeah, we'll see later on why that's important, why it has to be that way. But again, at this point, it's just the important thing is that you'll have one of those bits per column, and as long as you have 8 or fewer, you'll be at 24 bytes. If you have more than 8, you could bounce up above 24 bytes. Okay, that's the header section. On to the data section. And so here, every column with a non-null value requires a number of bytes depending on the column type. Null values will always consume 0 bytes on disk space, no matter what the type is. If it's null, it always consumes 0 bytes. And again, Postgres knows that it's null because of that null bitmap. So that's why you don't have to store anything special at this point. Every type also has an alignment, which will specify the hardware address that the type is allowed to start on. And I want to skip down a little bit to this part D, and there's a SQL query right here that we're going to take a look at and see how this query relates to the insertion that happens over here and these notes that happen above. So I'm on part D over here, looking at this select query over here. I'm going to change my terminal window over here to bring up an actual terminal here that we can look at the same time, and open up a pSQL connection. This query can be run in any pSQL session. It doesn't matter what the database is. So I've pasted the query right here into this session. This query says, select these 3 columns from this table PG_type. In Postgres, there are many tables that exist in every database that start with PG_. And these are like system tables that contain information about just how Postgres works. In this case, for every type in the database, so things like int8, char, int4, int2, these things over here in the schema, these are the types. This is going to tell us information that we will need about those types. So I'll hit enter, and maybe I'll zoom out a little bit so that it's formatted nicely. And then we can see the type names over here on the left-hand side, and this information about the alignment of that type and the type length. The type length is the actual number of bytes that it takes to store that particular type. In this case, we have int8 over here. int8 as our first column in this example table. And looking through this type name, again, I can type / to do a search in the pager environment, type int8 and hit enter, and it'll search for int8 for me. I can see that its alignment has type D, and this the type length is type 8. So I know that this int8 over here, this 0 right here that I'm inserting right here, which has type int8, this is going to take up 8 bytes. So just above each one of these values down here, I'm going to write an 8 right here, because this is the number of bytes, the type length that it's taking up. Similarly, for the char is the next one over here, a char. If I do over here a /, hit /, search for the character, you see that there are many different types that contain char somewhere inside of them. But the one that I'm looking for is just char by itself, this very first one over here, and this takes up just 1 byte. And so 1 byte. Int 4 will turn out to take 4 bytes. This 0 right here corresponds to int 4 because int 4 is the third column listed in the table, and this 0 right here is the third value that I'm inserting. The next one is an int 2 right here. And then over here, a 1, 2, 3, this has special type line. We don't know what this line does, what it represents. There will be on your quiz and midterm and homeworks various new types like this that we will not talk about in class at all. You'll just have to figure out like information about it by looking through the documentation. And again, over here, in order to figure out how much space it takes up, I'm going to type / look for the line. There is, in fact, line right here. In this case, its size is 24 bytes. So this whole thing right here is 24 bytes. And then we already saw that the null value over here is 0 bytes. So that's the raw space overall that our data is going to be taking in this data section. Any questions about where I gathered these numbers from for this insertion right here? Yes.
I have a question. How are some of the numbers negative?
Yeah, great question. Question is, why are some of the numbers like negative over here? So there's a lot of negative ones, even like this -2. And what's going on with that? The answer is that any type that can be variable in size is going to have its length be -1. So in this case, if I look for JSONB /JSONB right here, we get the -1 over here. This JSONB type is something built into Postgres for storing JSON, and JSON can be any size at all, from like an empty string all the way up to terabytes, like we saw with the Twitter assignment. And the -1 over here indicates that it's a variable size type. For the purposes of our quiz, and when I'm ever explicitly asking you to calculate the size of something, anything that has a variable size type will always have a null value over here, so you'll always just know that it takes up no space. The actual like format for how JSON or text or other things that are variable size, how those things are stored is complicated. You don't need to have that memorized. You can just know that if it has a -1 in its size, it means that it's variable length. And so I will always have it specified as null if there is one of these variable length things. Does that answer your question? Yes, great question. Okay, this is a good, I think, stopping point for us. We're pretty much out of time. So we'll pick up on this discussion on Thursday after your quiz. And again, on Thursday, I'll be here early, so you can start taking your quiz early if you would like to. If you have any questions about anything, I'll stick after class here to answer those. Otherwise, I will see you all on Thursday.